Okay, here we said clearly its principle. The reason is the following, as one of your friends pointed out. So let me look at this board. Okay. Dondu gene sanırım. Okay. So if U prime is 0, then S of alpha prime is 0. But 0 is just 0 times alpha prime, so that alpha prime is an eigenvector corresponding to the eigenvalue 0. Since this is an eigenvector, it's a principal direction. So alpha, the curve alpha, goes in a principal direction. Therefore, it's a principal curve. Okay, so that's the reason. When I prepare the notes, sometimes things seems very obvious, and actually they are obvious, but as time passes, obvious things turns to be not obvious usually. Okay, so let's erase this board. Okay. There is another example of principal curves. Let M be a surface of revolution. The meridians are and parallels. Parallels are principal curves. Surface of revolution. One example of surface of revolution. For example, take a half circle. What is the surface of revolution of this curve? Well, of course, you get a sphere. Okay. And if you take parallels and meridians, meridians means are actually they are just great circles. Circles on the surface sphere with largest possible diameter. So things like this. Of course, these are obtained by cutting the sphere by a plane, right? Which goes through the center of the circle. That planes are always perpendicular to the sphere. So they cut the sphere at an angle of pi over 2, right? So they orthogonally cut the plane. So right, just this plane, you cut through this plane, which cuts the sphere orthogonally. And what about parallels? You cut the plane by some other, sphere by some other planes. For example, you cut it with a plane like this. Okay. These are not great circles, but just some circles. Again, they are principal curves because the plane you cut this sphere to obtain this curve makes a constant angle with the sphere at all points. What is that angle? I mean, you can compute it, I guess. I mean, right. I don't know. If this, this is a parallel, you just cut it like this. The angle between the sphere and the plane is how much? The normal vector of the plane is this. The normal vector of the sphere is this. So this is the constant angle. But you see, this parallel and this parallel are basically the same. You just rotate this so that, I mean, if you think the South Pole is here, right, just rotate it this way, you will get a parallel circle. So actually, any circle on the sphere is a principal curve. Well, I mean, actually on the sphere, every curve is principal, right? So it's kind of useless. Nevertheless, okay. Yeah. But this is a stupid example. Why is that? Because on a sphere, every curve is principal, right? So I am just listing you some of them, but actually they are all principles. Nevertheless, it gives the idea. Let's take another curve. Suppose I take this. If you rotate this along the axis, you will get something like a okay, something like this. Vazo gibi. Yeah, my picture is not great, but you see, you understand. Okay. Parallels are this in this case. Parallels. And meridians are like this. Okay. These are principal curves. You cut it like this, either perpendicularly, or you cut it like this. In this case, the angle is not 90 degrees because this is V and this is U. But the angle is constant, right? It's constant. But if you cut it like this, then the plane is perpendicular to the surface. Tamam mı? Another one is the Taurus. Take a circle and rotate about this axis. You will get a torus. Okay, you will get a torus. Meridians and longitudes are these in this case. So this is a longitude, and meridian is something like this, right? So these are, so you just cut it either like this or you cut like this. vertically or horizontally, okay, you get principal curves. Okay, now we have a definition. Directions to a surface M in R3 in which kayıt yapıyorum değil mi? Okay. In which the normal curvature is 0 are called asymptotic directions. Like the one we just saw at the end of the proof, right? Along that was a principal direction, but the normal curvature was 0 in that case. We had the 0 eigenvalue, so that's an asymptotic direction. I mean, at a tangent space, you just pick a vector. Okay, so let's say this is the space, and you have a vector. In this direction, if the normal curvature is 0 in this direction, then it's an asymptotic direction. Okay. Oh, okay. I should say directions tangent to M. Okay. Directions tangent to M. Sorry. So, a tangent vector V is asymptotic if the normal curvature along that vector. So what is that normal curvature? It is the shape operator that this is 0. Okay. Let's see. Okay. Here is a lemma. Let P be a point on the surface M in P R3 if the Gaussian curvature is positive, then there are no asymptotic directions. If the Gaussian curvature is negative, then there are exactly two asymptotic directions. Asymptotic. At P and they are bisected by the principal direction. Principal direction at angle nu such that tangent minus K1P divided by K2P. If Gaussian curvature is 0, that direction is the direction is asymptotic. If P is a planar point, otherwise there is exactly one asymptotic direction. Okay. There is exactly one asymptotic direction, and it is also principal. Okay, now proof. Recall Euler's formula. Which says this: the normal curvature along a vector is just K1 P cosine squared nu plus K2 P sine squared nu. Right? What was this? You know, the tangent space to the surface at the point P has its principal directions E1 and E2, and these are just eigenvectors of the right shape operator. And if you take any vector u, which makes nu angle nu with, let's say, E1, then this vector, of course, can be written like this. It is just cosine nu plus, no, cosine nu E1 plus sine nu E2. Therefore, what is Ku? So I am just deriving Euler's formula. This is just S of U dot product with U, right? But what is S of U? Well, this is cosine nu E1 plus E2 dot product with the vector U, cosine nu E1 plus sine nu E2. These are just some real numbers, and these are eigenvectors. So this can be written as just cosine nu times S of E1. S of E1 is just K1 E1 plus sine nu times S of E2, that is just K2 E2, dot product with cosine nu E1 plus sine nu E2. And then what? Just take dot product of these two vectors, keeping in mind that E1 and E2 are unit orthonormal vectors, right? So E1 dot E1 is 1, E1 dot E2 is 0. So when you take the inner product, you get K1 times cosine nu E1 dot E1, which is 1. And then this inner product gives me 0. This one gives me 0. And the last one, inner product of these two, so it is K2 sine squared nu. Yes, that's it. Okay. Now let's erase this board. Okay, now let's now examine each case separately. Again, it is frozen. Okay. Yeah. Now, so let me write down what we had over there. So this one, K1 times cosine squared nu plus K2 times sine squared nu. Draw the picture here again one more time, E1, E2, and this is my vector U, and this is the angle nu. Okay, now case one is this. The Gaussian curvature is at this point, so this is the tangent space to the surface M, is positive. Well, Gaussian curvature is just the product of principal curvature. So this is K1 times K2. This is positive, means both are either positive or negative, right? So either K1 and K2 are both positive, or K1 and K2 are both negative. Well, in that case, if they are both positive or both negative, this expression is always positive or always negative, right? If K1 and K2 are both positive, then Ku is always positive. I mean, for all unit vectors. And if they are both negative, then this is negative, right? Because these are always positive numbers. So if you multiply them with negative numbers and add them up, you will get something negative. Then this is negative for all unit vectors. In this case, there is no vector along which the curvature is zero. Normal curvature is zero. Therefore, there are no asymptotic directions, right? Hence, there are no asymptotic in this case. Okay. Okay. Now, two. If Gaussian curvature, which is just K1 times K2, is negative, then if you letting Ku to zero, we wonder when this is zero. Well, that is Ku is this expression, so you just equate this to zero. So we get what? K1 times cosine squared nu plus K2 times sine squared nu is zero. From this, we see what? We see that tangent squared nu is just minus K1 over K2. This is negative, means one of them is positive, the other one is negative. Therefore, the ratio is also negative, but you have another negative sign here, so this is positive. So you can find V, right? What is that? V. This is just tangent inverse of square root of this positive number, right? So this is a positive number, therefore I can tangent inverse gives me the angle. So if U has the vector whose angle is nu, then that's an asymptotic direction. Yes. So I should say plus minus. Right? No, tangent takes values between pi over 2 and minus pi over 2. Yeah, yeah. So if we increase so yeah, right. One of them, if one of them is V, the other one is minus V. Yeah, yeah. Okay, what was the statement? No, it should be a little bit complicated than that one. If we let, let's say, V to be this, okay, tangent, okay, so we have this curve tangent inverse. So if no, this is the tangent curve. If one, this is one of the square roots, the other one is this one. So the angles between them, okay, yeah. In this case, yeah. All right. Okay, so so if this is nu, then this is minus nu, and yeah, okay. So we have this. This is one of the vectors, asymptotic vector. The other one is this one, minus nu. So this vector is not minus u, okay? Suppose this is u1, this is u2. It is not minus u. The angle is, it's negative, but this vector is not minus u1, okay? So this is not minus u1, but they make the same angle with one of the principal vectors. Therefore, I have two asymptotic directions, and they're bisected by one of the principal directions. the angle here is not necessarily 90 degrees, this angle. It is tangent inverse of something. Yeah, I mean, if you do this, then they're also bisected like this. Okay, yeah. Okay, so we are done in this case. So I should say plus minus. We have two angles, and they give me two directions like that. Okay. What about the third case? Let's change the board again. Okay, now if the Gaussian curvature is 0, then K1 times K2 is 0. So this means two things. Either both of them are 0 or one of them is 0. If K1 equals K2 equals 0, then P is a planar point. That's the definition of being a planar point. Along any direction, principal curvature is 0. If it is the case, then we call that point a planar point. If one of them is 0, if only, let's say, K2 is 0, then Ku, by the Euler's formula, this is just K1 times cosine squared nu, right? And when this is 0, we wonder when this is 0. And Ku is 0 only if nu is pi over 2 or minus pi over 2, right? So it means, okay, now E1 is this, E2 is this, then the angle is pi over 2. So I have, so nu is this much. Therefore, U and K, E2 are the same. In other words, the asymptotic direction is the principal direction. Hence, the asymptotic direction is a principal direction. And there is only one of them, okay? Of course, this one or this one, but you know, they are the same direction. So in this case, through this point, there passes only one asymptotic direction, not two. In all other cases, there are two or in this case, of course, if K1 and K2 are both 0, then every direction is asymptotic. There are either infinitely many or two of them or just one. Okay. Okay, I have only 7 minutes. Neyse şu tanımı da vereyim, ondan sonra bitireyim. Now here is a definition. A regular curve alpha in M is an asymptotic curve provided that its velocity vector alpha prime always points in an asymptotic direction. Thus, alpha is asymptotic if and only if the normal curvature along alpha prime, which is just by definition shape operator applied to alpha prime, that alpha prime is 0. Since S of alpha prime is just U prime in this case, if it is asymptotic, why is that? S of alpha prime is, okay, so what we mean by this is this d over dt of u of alpha t, right? By definition, it is this one. The covariant derivative of u along alpha prime. So this is 0 means alpha is asymptotic if and only if u prime that alpha prime is 0. So that's a characterization of asymptotic curves. Velocity vectors are always perpendicular to change, well, the derivative of u along alpha prime. And here's a remark. Let me also write that down. And then I'll finish. If alpha is asymptotic, since alpha is tangent to M, we have Okay, şunu şöyle yazayım. Let alfa be asymptotic olsun. Be asymptotic. Okay. Since alpha is tangent to M, we have this, right? Tangent vector, dot product with the normal vector is 0. Taking derivative, we get what? Alpha double prime dot U plus U alpha prime U prime. But alpha double prime, if it is asymptotic, I have this. Therefore, the second term is 0. So this is 0 since alpha is asymptotic. This implies alpha double prime dot U prime is 0. Hence, dot U is 0. Yeah. So a curve is asymptotic, then if its second derivative acceleration vector is always perpendicular to U. Okay, so that's it, I guess. Okay. Sorusu olan var mı? Okay, let me stop the recording then.